Okay, so now I want to look at a very specific set of groups that's going to play a big role for us. And these are going to be the symmetric groups, okay? And so I'll define the most general thing at first, and then we'll restrict down to finite ones. But generally, if X is a set, we let Sx equal to the set of all f, f going from X to X, and f is bijection, so 1 to 1 and onto. So essentially it just takes X and moves it around, so to speak. So in particular, these things are called, this is the set of permutations of X. Okay, so this is what this set is. This is clearly a group, so the identity function from X to X, right? So this is just the identity function on an X equals X. It just does nothing. That is the identity element in this group. The operation is composition, so FG is really going to be F compose G. Now this is important because we are doing right to left function composition in this class, and if you watch some of the videos, the visual group guy actually does left to right, and so that changes some things, and you have to be a little bit careful about that. And then finally, when we have bijections, right? So F inverse exists as a function, right? So F inverse is just F inverse as a function, right? So anyway, this is a group, right? Because if I take two bijections and I compose them, I get a bijection. And of course, function composition is associative. It's definitely not commutative, right? But it is associative, and let's just make sure we understand that. So I want to say FGH, right, is supposed to be FGH, right? That's part of what we need to show here. So let's just write this out in terms of composition. So if I'm going to show that this function is equal to that one, well, I just need to show that on every X, it does the same thing. But then how do you interpret this? This is F of G of H of X. That's the way composition is defined, right? It's this function composed with that one. And then this is going to be F of G of H of X. Again, that's how function composition is defined, right? And now we're going to unpack it in the other direction, right? So this is F of G composed H of X. And this, of course, is just F composed G composed H of X. So, I mean, nothing interesting going on here. We're just unpacking what it means to be F of G of X, right? I mean, let's just make sure we get that. I mean, this is everyone should get this, but, F of G of X just means F of G of X, right? So that's all I'm using. Okay, so definitely we have associativity, right? Good. Anyway, so the group, right? So the group Sx is the set Sx together with composition, that's the multiplication here, together with the identity function. Okay, and as usual, I'll identify that as E. I'll typically write that as a dot or just leave it out, right? And just remember that our composition is always right to left, right? So that's actually important. Okay, so now we're going to drop down to finite permutation groups. So studying infinite permutation groups is really interesting, but in general, it's kind of out of the scope of what we're doing here. Not entirely. I guess we'll look at it. We'll look at one case where we apply this. But the Sn is now what I would like to do is say Sn is just the permutations of n, and that would be a perfectly good thing to do. Remembering that n is equal to n minus 1, so that is a set with n objects in it. But usually, instead of using this set, we say that Sn is the set of permutations of not 0 through n minus 1, but 1 through n. Okay, and that's just, I don't know, just the way things are. So generally when we write Sn, we mean that, but it could be any permutations of n many things. It really doesn't matter what we call the things. So in fact, sometimes in the book you might even see A, B, C, D instead of 1, 2, 3, 4, right? Okay, and there's some notation for these. So let's sort of restrict down to say S5, right? So I'm looking at functions from 5 to 5. And so one way you could write them is like this: 1, 2, 3, 4, 5. Whoops. And I just say where things get sent. So this could go to 2, 4, 3, 5, 1, for example, right? So we could just say that's my permutation, right? And so it's saying 1 gets sent to 2, 2 gets sent to 4, 3 gets sent to 3, 4 gets to 5, 5 goes to 1, right? So that's a way of doing permutations, right? So let's say this is sigma, right? And let's say tau is, so I'll write another one, 1, 2, 3, 4, 5. And let's just make up something else, 5, 4. I'll just go backwards. No, okay, let's move 3. Let's see, what am I missing? 3. Okay, so there's another one, right? And then, when I say tau sigma, I mean do sigma first and then tau, right? So now we can think about what that is. So 1, 2, 3, 4, 5. So where does 1 get sent? So we're doing sigma first. 1 gets sent to 2, 2 goes to 4. So that goes to, whoops, that goes to 4. 2 gets sent to 4, 4 goes to 1. So that gets sent to 1. 3 goes to 3, 3 goes to 2. 4 goes to 5, 5 goes to 3. 1 gets sent to the only thing it can be sent to, but let's just work it through. 1 goes to 2, 2 goes, oops, sorry, 5, right? 5 gets sent to the only thing. So 5 goes to 1, 1 goes to 5. There we go. Right, so 5 actually goes to 5, right? And so that's different than sigma tau, right? So, I mean, this shows you that this is not commutative, right? That shouldn't be surprising, but here we're going to do tau first, right? So 1 goes to 5, 5 goes to 1, so 1 actually goes to 1. Tau first, 2 goes to 4, 4 goes to 5, so 2 goes to 5. 3 goes to 2, 2 goes to 4, so 3 goes to 4. 4 goes to 1, 1 goes to 2, and then 5 goes to 3, 3 goes to 3, right? And again, you have to have all the numbers because these are permutations, right? So it's got to be 1 to 1 and on to. Okay, so that's one way of writing permutations. Now another way, and this is going to be really important, is to write them in something called cycle notation. Okay, so for any permutation, this is in particular for a finite set, right? We can do this. We can say, and we kind of focus on here, but it doesn't really matter what we start with, right? But we have an order here, 1, 2, 3, 4, right? So I'm just going to pick one. It really doesn't matter what you start with. So I'm going to say, where does 1 go, right? So let's take sigma, okay? So I'm going to write sigma in a slightly different way. Where does 1 go? So 1 goes to 2, okay? So 1 goes to 2, so I'm just going to write it like that. Where does 2 go? 2 goes to 4, 2 goes to 4. Where does 4 go? 4 goes to 5. Okay, so it goes to 5. Where does 5 go? Well, 5 goes back to 1, right? And, as long as you keep getting different things, this has got to stop and go back to something earlier, because otherwise you'd have an infinite set of things. I mean, we've only got 5, right? Now this isn't quite, in some sense, what are we missing here? We're missing 3, and we could write that down as an extra thing like this. 3 just goes to 3, right? Or in this case, you could just, ignore that, right? And so this is another way of writing sigma. So this tells me everything. This tells me, like what is sigma of 4, right? I just say 4 goes to 5, so it's 5. Now notice that's the same, right? Here sigma 4 goes to 5, right? So it's just like that. Let's do the same for tau, right? So tau. So again, we can start at 1. Again, it doesn't matter what you start with. You can start at anything, but it's sort of natural to start at 1. So 1 goes to 5. Where does 5 go? Well, 5 goes to 3. Where does 3 go? 3 goes to 2. Okay, where does 2 go? 2 goes to 4. Where does 4 go? 4 goes to 1, right? So this actually involves all of these numbers in there. So it's like that. Good, and then we can combine these, right? So let's actually compute this tau sigma again. So let's compute tau sigma this way. So now we've got these two things. And so I'm going to write tau here. So 1, 5, 3, 2, 4. And 1, 2, 4, 5, 1, 2, 4, 5, right? Now let's compute tau sigma in this kind of notation. So again, I start with 1. Again, this is something students get confused about. It doesn't matter what I start with. I could start with 5, but I'm just 1 is a natural thing. 1 goes to 2. Now what does 2 do? 2 goes to 4. So 1 goes to 4 in the composition, right? Now I say, what does 4 do? Well, 4 goes to 5. 5 goes to 3. So 4 goes to 3. And notice we're putting stuff in here first and then out there. And then what's the next thing? So 3, right? So now 3 over here, it's not mentioned, so 3 just doesn't do anything, right? So don't worry about 3 there. And then 3 goes to 2, right? So it's like that. And then where does 2 go? Well, 2 goes to 4, 4 goes to 1, so it goes back, right? Like that. And so what actually gets fixed here is 5, right? So let's just double check. 5 goes to 1, 1 goes to 5, right? So 5 is fixed. If that hadn't happened, we would have to have a mistake, right? I mean, so one thing you can do is sort of check for mistakes along the way. So I'm saying that 1, and let's just check, right? We did this above, tau, so here's tau sigma here. So 1 goes to 4, 2 goes to 1. So when we read this, right, we come out this side, we have to go back. So it goes around like that, right? 3 goes to 2, right? 4 goes to 3, right? 5 goes to 5, right? So that's what we have, okay? So it's good practice to do these. Now, of course, if I flip these around and I look at sigma tau, right? Let's just do that. We'll get something different, and we should again, get a different representation for what we had up here. So writing this out, I'm just going to write everything out again. So 1, 2, 4, 5, and 1, 5, 3, 2, 4, right? And so again, I'll start with 1, right? So 1 goes to 5, 5 goes to 1, right? So actually, we stop there, right? Now we need to start a new one, right? Because that one closed off. So what does 2 do? 2 goes, and again, it doesn't, I'm picking the next one. I can pick anything I want as long as it's not in this first one. So here 2 goes to 4, and then 4 goes to 5. So, 2 goes to 4, and then 4 goes to 5. So 2 goes to 5, right? And then now sometimes it's easy to make mistakes. So, it would actually be nice to make a mistake, and I could show you how you can recognize it. But let's see. So 5 goes to 3. 3 just sits there, right? So it's just 5 goes to 3. Now what happens to 3? 3 goes to 2. 2 goes to 4. So 3 goes to 4, right? And now we're out of numbers, so 4 had better go back to 2, right? So 4 goes to 2. 4 goes to 1. 1 goes to 2, right? So see, I almost made a mistake there, right? 4 goes to 1. 4 goes to 1. 1 goes to 2, right? So it's like that. So here we get this, and again, we could just ignore this 1 and just write 2, 5, 3, 4, right? Like that. Good. Okay, so one thing to note here, I mean, clearly these are non-commutative in general, but if we have disjoint cycles, okay, so let's say we have 1, 3, and 2, 4, 5, right? Okay, so these are disjoint. Then it doesn't matter which order we write these things in, right? So let's just see that. So if we multiply these two things together, right, what do we actually get? Well, what am I saying? What do we get? Let's write this, because that's what we get, right? There it is right there. Let's just write it out like this in the other style, 2, 3, 4, 5. Let's just see what happens here. So 1 doesn't do anything here, it just stays 1. So 1 goes to 3, right? 3 doesn't do anything here, just something happens there, so it goes to 1. 2 goes to 4, right? 4 goes to 5, and 5 goes to 2, right? So this is my, so forget these earlier sigmas and taus. It's called this one sigma now. So this is also sigma. The computation I did just now wouldn't be any different if I had 2, 4, 5, 1, 3, because those don't have any, nothing in common between those two things, right? So as long as we have disjoint cycles, it doesn't matter what order you write them in. So that's really important. So when we're actually decomposing this thing into cycles, so let's actually do this backwards. Like, let's take this thing and decompose it into a cycle, right? And let me just start with some random number instead. Let me start with 3, just for the heck of it, right? So 3 goes to, let me not start with 3, because I want to be even more. Let me start with 4. Okay, 4 goes to 5, right? 5 goes to 2, 2 goes to 4, right? So there's my cycle. And then I can come back here and I don't know. So 1 and 3 are missing, so I'll just grab 3 for the heck of it. 3 goes to 1, 1 goes to 3, right? So I get that. And so, here's what looks like maybe a different decomposition, right? But really the order doesn't matter. And also 1, 3 is the same as 3, 1, right? And 4, 5, 2 is the same as 2, 4, 5, because all you're doing is moving 2 to 4, 4 to 5, 5 to 2, right? So these, this is a cycle here, right? So the order in which you can always cycle these things around, right? Move them. I mean, not, sorry, you move 5 to there, right? 2 would go there, 4 would go there, right? Things like that. Hopefully that's clear. You'll get lots of practice in the exercises working with these things. Let's see, some important things here are, let me just see real quick. So I did that. So the length of a cycle is the order, right? If this is my, let's say this, so here's sigma, and I've broken it into these two cycles, right? So let's say this is tau 1 and tau 2, right? Those two cycles, tau 1 and tau 2. Okay, well, we can see that tau 1 has order 3, right? And in particular, we would get tau 1, and then we do tau with itself again, right? And then when we do it again, we get tau 1 cubed, but this is going to be the identity function, right? So let's just verify that, right? So, if I do 4, 5, 2, right? That's my tau 1. So this is tau 1, right? So let's do it twice. So tau 1, right? So I'm just going to do it twice. So 4, 5, 2, 4, 5, 2. What actually happens? Well, 1 and 3 don't do anything because they're not there, right? But so let's start with 2 because it's the smallest thing. So 2 goes to 4, 4 goes to 2, right? So it just, nothing happens there. I mean, it's just 2 stays fixed when in this composition, right? And then 4 goes to 5, so 4 goes to 5. Oh, did I do something wrong? Oh, let me see. Sorry, let's look at this again. See, there I think I made a mistake, so let's try this again. So let's start with 2. 2 goes to 4, 4 goes to 5. Sorry, see, I made a mistake there. 5 goes to 2, 2 goes to 4. Okay, sorry, yeah, we get this. Yeah, so we get another 3 cycles, so that shouldn't surprise me too much. So let's do tau 1 cubed, right? So I'm going to do this, so 2, 5, 4, and I'm going to do tau 1 again, which was 4, 5, 2. Okay, and let's just see. Notice, by the way, that these are just reversed from each other, so maybe that's a hint here. So 2 goes to 4, 4 goes to 2, right? So now 2 stays fixed, right? 5 goes to 2, 2 goes to 5, so 5 just stays fixed, right? 4 goes to 5, 5 goes to 4, right? So it stays fixed. Okay. So the order of a cycle of length 3 is 3. I mean, I guess that's not surprising because we can visualize us moving things around, right? So it'd be a cycle. We can think of it like a cycle group like that. Another thing we see here is that, given a, so if tau equals, let's say, 3, 4, 5, 1, right? The inverse is going to be what you get by flipping this around, 1, 5, 4, 3, right? So that's another thing we can see here. So this is a very, very concrete group where we can, get our hands on the elements very simply, right? And this makes sense because 3 is getting sent to 4 here, 4 is getting sent to 3. That's what happens when you reverse the order, right? So that they're undoing each other, right? So that's the order, right? So this one have order of this tau would be 4, right? Now another thing is that we can take any tau and break it into swaps, single swaps, right? So if I take, let me take again this 3, 4, 5, 1, right? So there's a thing. And there's actually a couple of ways of doing it. So let me do this one the way I have it written here. And I could think, if I thought about it for a little bit, I could think about the other way of doing it. Maybe, well, I don't know. Well, maybe we'll do it in class or something. But here I'm just saying, in order to break it into swaps, right, I'm just going to fix the n1, which is 3 in this case, the first thing, right? And I'm going to write the 1 there, right? and then I'm going to keep writing the 3. Oh, actually, I have both. I have two different ways of doing it here. So I'm going to write the 3, and I'm going to write the 5, right? Okay, and then I'm going to write the 3, and then I'm going to write the 4, like that, right? And so notice that this has length 4, it has order 4, but it requires 3 2 cycles to write it down here. I mean, I don't know about requires. Maybe there's some other way, right? But there's 3 2 cycles here. And let's just verify that this is the same, right? So what happens with this way of breaking things up? Well, 1, what happens to 1? Well, you go all the way down and 1 just goes to 3, right? And that's what happens, right? You can kind of see why this works, right? What happens to 4, right? Well, so 4 goes to 3, and then 3 goes to 5, right? And then it's not moved again, right? So 4 goes to 5. And then 5 goes to 3, and then 3 goes to 1, right? So 5 goes to 1, right? So that's exactly what we had here. So the other way of doing it is like this. I could write, so it's 3, 4, and then the next pair would be 4, 5, and then the next pair would be 5, 5, 1, I guess. Okay, so just sort of stepping, you're kind of taking that group, then that group, right? So let's see that that's the same. And there's nothing special about being link 4, right? In the notes, I have this in general. So let's just verify this too. So 1 goes to 5, 5 goes to 4, 4 goes to 3, right? So 1 goes to 3. Then we have, what's the next one I want to see? So 1 went to 3. Let's see where 3 goes, right? I guess I'm just going in order, right? So 3 doesn't do anything, it goes to 4, right? 3 goes to 4. And where does 4 go? Well, 4 doesn't do anything here. 4 goes to 5, and that doesn't do anything else, so 4 goes to 5, and we're done. Again, remember, we're reading in this direction, all right? We're composing our functions. These are actually functions, and we're composing them. These are not disjoint from each other, so the order matters, right? If we change the order here, we'll get different things. So this was two way of decomposing this length 4 cycle into a multiplication of 3 swaps or 2 cycles. Okay, and there's an important thing here called the it's like the parity or the I forget, actually now I'm forgetting what we actually call it. I guess I just call it parity. Like we say they're either odd or even cycles, right? So the point is, no matter how we break this up into a sequence of swaps, like this sequence of swaps that gave this thing has 3 of them, right? So no matter how I do it with a sequence of swaps, because I could just swap the same thing over and over, put a bunch more, but it's always going to be odd, right? Because here's one that works and it's odd, so every other way of writing this thing will be odd. So if I have an in length cycle, the number of swaps required will be n minus 1, and the minimal number of swaps required will be n minus 1, right? So you change, this is an even length cycle, it's got odd parity, right? So this odd and evenness of these things is going to be really important. And there's a proof in the book, and I don't know really like slick proof of this that's insightful. I mean, the proof in the book is good, but it's not beautiful in any sense, right? And I'm going to give you another proof, which is kind of nice, but it also kind of uses some extra stuff. And so I'm going to do a proof that uses some linear algebra. And in fact, I'm just going to sort of show it to you here, right? So we can always code in swaps by like let's say that I'm looking at 1, 2, 3, 4, right? And I want to swap some things around, right? So I want to make this, I'll like swap these first 2 to make it 2, 1, and then 4, 3, right? So I did those 2 swaps there, okay? Well, I can kind of do this with a matrix. So I swapped the first 2 things. So I start with the identity matrix. And what I'm going to do is I'm just going to swap the corresponding columns just in the way I'm wanting to swap those things, right? So any permutation I do of these things, I can just permute the columns in the corresponding way, right? So oops, this is going to become 0, 1, 0, 0, 1, 0, 0, 0, and then 0, 0, 0, 1, 0, 0, 1, 0, right? So I'll get that matrix. So this is going to be, so there's this permutation sigma, right? So what is the actual permutation? It's going to swap 2 and 1. It's going to swap 3 and 4, right? That's what it's doing. So here's the corresponding matrix, which maybe I'll call M sigma, right? Where I'm just swapping the corresponding rows. If I did the same swap on the, columns, but if I did the same swap on the rows, I would get exactly the same matrix. It actually doesn't matter which way I do the swapping. And if I run M sigma on, the vector 1, 2, 3, 4, it's going to do those swaps. It's going to give me 2, 1, 3, 4, 3. So it's actually going to produce that permutation, right? So this matrix implements that particular permutation, okay? And the point is now, and I guess in some sense I'm jumping the gun because later in the next topic is isomorphisms, and that's kind of what I'm using here. So I've got this map that takes me from Sn to permutation matrices, but those are all, I mean, if you think about this thing, these are all going to be matrices in GLN of R, right? These will always be invertible matrices. I mean, swapping is part of what you do is an elementary row operation, so those are always invertible matrices. And this is actually a isomorphism. So if I take sigma, if I take sigma tau and I map it, to M sigma tau, well, what I'm going to get here is M sigma times M tau, right? And that's a nice argument to consider. I think maybe I put that on an exam once because this is actually a nice thing just to sort of work through on your own. But the point is that this is actually an isomorphism. So we're embedding this as a subgroup of GL in R. Okay, and then the next thing is that the map, which is the determinant map. Now the determinant of every one of these things is plus or minus 1, depending on the even or oddness of the cycle here, right? So if I say, what's the parity of this thing? I'm not even sure how I denote that. The do we call it anything? Like how many swaps I need to make here, right? So anyway, the determinant of these, so the determinant of M sigma will be minus 1 to the, I'm not really sure what to call it. I'll call it parity of sigma, right? So that could either be 0 or 1, right? So if it's even, it'll be 0. If it's odd, it'll be 1. So it's either plus or minus 1, right? And so this is actually mapping into Z2 as a group. Let's see, as an additive group, like plus or minus 1. So it's not really Z2, it's an isomorphic copy of Z2. It's 1 and minus 1. We get all sorts of fun things. And this is a group under multiplication, right? So 1 and minus 1 is a group under multiplication. So it's isomorphic, of course, to Z2, right, which is the corresponding additive group. Okay, but the point is that we have this map now that's taking sigma in. If I combine these two things, over here to Z2, and this is what the determinant composed with this phi map, right? And this is what's called a I mean, it's an isomorphic copy. No, it's a homomorphism, right, from Sn into Z2. And I guess really here I actually don't need to say, maybe this is the point too. I don't need to say the parity. What I really want to say is K, where sigma is written with K swaps. Doesn't matter how I write it with K swaps. If I use K swaps, I have minus 1 to the K. That's a theorem from linear algebra, right? So if I swap rows in my matrix, K many times, then what does that do to the determinant? It multiplies it by minus 1 to the K, right? So that's sort of what's being used there. So it doesn't matter which way I write sigma. That's kind of the whole point. It doesn't matter which way I write sigma. This will always map to the same value over here, plus or minus 1. And so that shows me that no matter which way I write this, I always get either an odd or even, right? Because either I always getting minus 1 to the K is 1, or I'm getting minus 1 to the K is minus 1, right? So either it's always even or always odd. That's kind of the point. So there's there's a proof that the way you break up the permutation into 2 cycles at least the parity of that doesn't depend on how you break it up, right? So that's kind of the point. Okay, good. Okay, there's one more little subtopic here, and that is you can view, and we're going to show below that any group can be embedded, any finite group can be embedded into to SN. But the dihedral group sort of embeds very naturally into SN. So what you can do is you can label the vertices of the thing that you're like. This would be D5, right? That I'm looking at here, and you can label these vertices. And so here's D5, here's D6. I guess I've got kind of two different cases here. The rotations are going to correspond to just moving, vertex 0 to 1, 1 to 2, 2 to 3, etc. Right? So the R, the rotation, right, will just be given by this permutation of the vertices. And then the flip around here, right here, 1 will be sent to n minus 1, and then you keep going down here. 1 gets sent to n minus 1. You look at the way things go down there. So it's one of these two things, right? Will be that vertical flip, right? And then those two things will generate the entire, dihedral group as always, right? Again, they satisfy the relations that Rn equals E, right? And S squared equals E, and RS equals E, right? So, and that's all you need for the dihedral group. So that's always what that thing, I mean, any group generated by two things that satisfies those three relations and nothing else, right, is Dn. I mean, that's not something we've actually proved, but it's just a useful way to think about it. And as you get the feeling for it, you'll see that more and more. And when we talk about isomorphisms, we can make that a little bit more clear. But anyway, that's going to be our introduction to the symmetric groups. Okay, enjoy.